fields, forces, and energy. Let's jump into a little bit of review. So again, you see these review questions, pause them, think of the answer in your head, unpause and see if you're right. First one is, what is a force? We have mentioned it in Objective 1, but it's also old. What is a force? A force is a push or a pull. This one, basically look at each picture and think if it's a contact or non-contact force. The apple falling, it's being pulled toward the ground, even though they're not touching. Its gravity is a non-contact. Pulling on a rope, it's touching, that's contact. Magnets are not touching the metal, but they are pulling them, so that's non-contact. Touching here and here, contact. Touching here and here, also contact. What two factors determine the strength of gravity between objects? Pause and see if you remember. Two factors are distance. The closer they are, the stronger it is, and mass. The heavier they are, the more gravity there is. So, we're going to talk about vectors. When we're talking about forces, we're going to often illustrate them as a vector. And before I explain what those are, here's a vector, the blue line. Here's a vector, the green line. And here's one, the red line. My guess is they're so intuitive that you can figure out some things. So looking at those three vectors, which one do you think is the strongest? Yeah, it's 3, and the reason you can tell it's the strongest is because it's the longest line. So the length of the line tells you how strong, or the magnitude, that's another way of saying how strong the vector is. The other thing that you can see there is the arrows. Well, of course the arrow is going to tell you which way that force is moving. In this case, they're all moving to the right. In the bottom picture with the car and the tow truck, well, it's moving up and to the left. That arrow just tells me that. I don't need to know anything. I just follow the arrow, and then I know which way that the force is moving. A vector field is just a map of all the vectors over a given space or area. If you were here for the magnet lab, you saw that. We sprinkled those metal filings over the piece of paper that was on a magnet, and they just moved on their own and made this magnetic field. We can observe these in non-contact forces. That's why we used magnets in our lab. In this vector field here, you can see up here we have some strong vectors that are moving down to the right, some strong vectors down here moving up and to the right, and some really weak vectors. It looks like they're all pointing to like the middle. But just shows you how the forces strong they are and which way they move in different parts of the vector field or the map. Oops, sorry. Go ahead and pause while you put that in your notes. So, pause when you see these questions, think of the answer, then unpause to see if you're right. What two things do vectors show us about a force? The direction from the arrow and the length of the line shows us the magnitude or strength. You really can't do that on your own, so I'll skip that one for you. So fields for non-contact forces. Remember, objects are not touching. A field is the space around an object where that force exists. The Earth has a gravitational field where other objects experience the pull from Earth's gravity. Eventually, if you go far enough into space, you're not feeling Earth's gravity, really. You're feeling another planet you get near to, the sun, whatever. Technically, fields never disappear, but you really don't feel their impact when you get far enough away. Go ahead and pause while you put this in there. If you want, you can Google search this and have your song break, but as always, if you're doing makeup to get caught up, I don't make you listen. I'm going to get it caught up quick. So, some different types of vector force fields. Gravitational fields, we're probably pretty familiar with that. And technically, gravity exists between every two objects in this room, in your room, wherever you're at, but you only feel the gravity, really, of the Earth because it's so massive and we're so close to it. We're right there. We're right at the ground. So when we look at this picture here, if we're looking at the picture on the left, those are our vector fields. Strong arrows all pointing straight to the ground. If we go outside the Earth, same thing. They're all pointing towards there because Earth's big. It's massive and it's pulling things towards it. Electric fields are areas around electrically charged particles. Notice this. If it's a positively charged particle, the forces are moving away from it. And if it's a negatively charged, the forces are moving towards it. Over here, we have a positive and a negative. Opposites attract, so in the middle, they're going towards each other, and away, well, positives are still trying to leave, but you can see they're kind of bending toward the negative side, and the forces around the negative are trying to go toward it, but they're bending toward the positive side too. If we have two like charges, this picture down at the bottom here would be the same if they were two negatives or two positives. Like charges, two positives, two negatives, repel. So notice how they won't even touch their vectors, their forces. This is a press pause when you see these to answer in your head, but remember, opposites, like even people, they say opposites attract, well then like charges repel or push apart. And I just said opposite charges attract. Pause while you put this in your notes. So, what is stored in a force field, those vector fields we talked about? Potential energy. Remember when we held our magnets together, we used our force to make a positive and positive side next to each other? As soon as we let go, it moved because they stored potential energy. Same thing. We talked about gravitational potential energy all year. You hold an object up in the air, it has the potential to fall. An object, hopefully we remember this, has more potential energy when it can travel furthest. So the higher up something is, the more potential energy it's going to have. And with charges, the stronger the electric charge, the more it's going to move when it's let go as well. Pause while you add this to your notes. All right, your notes should have all this, and you should be good.